We're now going to begin Chapter 6, which is the study of the applications of integrals. This material is sometimes covered in Calculus 1 and sometimes covered in Calculus 2, so I've included the first three sections in both playlists. In Calculus 1, it is not typical to go beyond volumes of revolution, so we'll stop after that. However, you can find the remainder of this chapter in the Calculus 2 playlist. What we're talking about in Chapter 6 are the applications of the integral, and there are many, from economics to medicine to biology, population growth, radioactive decay, physics. Just about any situation that you can imagine being modeled with mathematics can use calculus to describe rates of change and other applications. In this first section, we start by taking a closer look at area between a curve and the independent axis. In the first section, what we're going to do is we're going to translate that idea of area between the curve and the independent axis into area between two curves. Now, this means that we'll have one function sort of above another function. And instead of knowing the area between the curve and the independent axis, the net area, we want to know how much area is between the two curves. We'll look at situations where one is above and one is below. We'll also look at functions that are a function of y, where instead it's a graph to the right and the graph to the left, and we're looking for the area between them. Most can be done either way, but I will tell you that it is often the case that one is easier than the other. When we're doing this, you might realize that the easiest way to find the area between the two curves is to instead find the net area that's under the lower function and the net area that's under the upper function, and to subtract the area for the lower function from the area from the upper function. And in fact, that's what we do. Let's take a look now at the learning objectives for this section. When we're looking at the learning objectives, remember that we are going to do this both for functions of x, where we look at graphs above and below, and for functions that are functions of y, the dependent variable, meaning that instead of above and below, we'll be looking at left and right. Because the second type is a function of y, the differential will have to be dy. The limits of integration, since these will all be definite integrals, will have to be y values. We'll talk about how to determine which is the easier one to do or whether it matters. If it doesn't matter, it's a personal choice, and most students tend to choose to integrate with respect to x. But there are times when it is far easier to integrate with respect to y. The learning objectives are pretty straightforward. We're going to find the area of a region between two curves, whether it's above and below or left and right, by integrating with respect to the independent variable. That would be the above below. We'll find the area of a compound region. Now, by compound region, we mean that perhaps what's above and what's below switches at some point. So we'll have to find the area between in both situations and combine them together. Then we'll switch our attention to finding the area between two curves by integrating with respect to the dependent variable, the y, instead. Let me share my screen with you and we can get started. We're going to start by allowing our functions to be functions of the independent variable x, and they're going to be continuous over an interval from a to b, so that they are, in fact, both differentiable. And we're going to set it such that the graph of f of x is greater than or equal to the graph of g of x for all the values of x between a and b. In other words, the graph, the y values on the function f, are all greater or equal to the y values on the function of g, which you can see here. The interval from A to B can be selected and cut off with a vertical line at x equal A and a vertical line at x equal B. What we want to find is the area between the two curves. The way that we compute it, of course, is to find the area that is underneath the f-axis and between it and the x-axis, the net area, whether it's all above or all below or a mixture of the two. And then we find the area that is underneath the g-axis. Note that they do have some area in common. And then we subtract the area, net area between the f function and the independent axis, and we subtract the g from the f. In other words, we end up with the region between by subtracting the lower section from all of it. There are several applets that I'll introduce you to that can help you to do this. In this particular graph here, we have a multiple of the sine function, and this, I believe, is a fifth-degree polynomial. And we want to know the area that's between the two. So when we're looking at this, we can take a look with some applets in order to approximate it. One of the applets you can see right here, which is giving us that fifth-degree polynomial and a multiple of the sine function. Basically, this is just a left Riemann sum, though it could have been done with a right Riemann sum or a midpoint or some other technique for approximating the area under a curve. What we have in the directions over here towards the top is we have the sum of the Riemann sum here for f. This 227.5-ish represents the area that is shaded in blue. This, of course, is the net area under the fifth-degree polynomial and the independent axis. And then a little bit further down in the directions, you see that we have the same thing for the function g, which is 15 sine of x divided by 4. The area between the g function and the independent axis is about 27 units. And then at the very bottom, we see that we're subtracting the area under the lower function from the area under the upper function. And this gives us the net area between the two functions. Let's talk about how we approximate it. Now that you've seen the applet using a left Riemann sum, let's look more closely at what's happening. You'll notice that we've drawn a series of rectangular boxes. I typically call these strips. The strip is running from the lower curve to the upper curve, which means each strip is vertically oriented. The width of each strip becomes the change in the x value, delta x, which is equal to dx. So this value right here is our differential when we integrate. This is dx right here on the end. Then you can see that the length of the strip is actually the y value of the upper function minus the y value of the lower function. So that the length of the strip coming right here becomes f of x sub whatever it is, x sub 1, say, minus g of x sub 1. In order to find the area of the strip, we multiply the height or length of it by the differential dx. And then you know what we're going to do. It's a Riemann sum. We add them all up from the left to the right, and then take the limit as the number of rectangles or strips goes to infinity, which is the same as saying that the width of each strip goes to 0. This gives us the limit of a Riemann sum, which is a definite integral. And the interval over which we're integrating is from A to B. You can see over here that I've drawn likewise the boxes that are between the fifth-degree polynomial and the sine function. Again, the width of each box becomes the differential dx. And the difference between the y values on the upper minus the lower function become the length of the box. And then the area of the box is length times width. And when we add them up, we get the approximation for the area between the two curves. In this example right here, what I've done is I've separated out the two separate pictures. Here is the area, the net area, using a left Riemann sum that is under the fifth degree polynomial. This green shaded area in the middle is the area, the net area, under the lower function g of x. And to get the area between them, I want to take this area in blue and subtract the area in green. And when I'm done, that will give me just the area that's between the two curves, which includes the small strip right there. Here are the links to the two applets that I recommend using for finding the area between two curves. The first one is the one I showed you before, which is Desmos. And the second one is a GeoGebra one. Let's take a look at the GeoGebra one now. In the GeoGebra one, you actually have the opportunity to watch the amount of area building by sliding the slider at C until they intersect. Notice that what we're trying to find is the area from -1 to 2 between the two functions. And what we do is we take the upper function, which in this case is the line x plus 2, and we subtract the y value on the lower function, which is, of course, the expression x squared. Then we multiply by the differential dx. Notice that there should be parentheses around the integrand there. What you can do is you can take a hold of the slider and move it across until you reach the point where they intersect. And at that point, the areas should match. And the area is given exactly as 4.5. Let's go ahead and introduce the definite integral that gives us the difference in area between an upper and a lower function. We'll let our functions f and g be continuous, such that f of x is always above g of x, over a closed interval from a to b. We'll let r denote the region bounded above by the graph of f of x and below by the graph of g of x. In other words, this area in here is r, and it's shaded blue. On the left, it's bounded by the vertical line at the left endpoint of the interval, x equal a. And on the right, by the vertical line at the right endpoint of the interval, x equal b. Then we can find the area of the region R between the two curves by integrating from a to b of f of x minus g of x, which of course is equivalent, because of the difference rule, to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Whether you use this formula in the center or the one on the right is completely up to you. They're both correct and both will work in all cases. In the right one, we've simply split it into two integrals. Here, you're just keeping them together, but you're still integrating, so you'll have multiple terms in the antiderivative function. Now, there are occasions where the points A and B may not be given. Instead, what may happen is that the curves intersect. And we can find our A and B by finding those points of intersection where they touch or cross. When they touch or cross, the y value is on both graphs. So we can set the functions equal to each other and solve for the x coordinate that causes that to happen. And then, of course, we can find the values for A and B. Curves may not intersect in all cases, but in those situations, if they don't intersect, You have to be told the interval over which to find the area between the two curves. If it's not a case of intersection, you have to be told what A and B are. We're going to assume that f of x is always above the graph of g of x. Now, obviously, which one's f and which one's g is totally arbitrary. It could be g above f. But we'll simply make it our habit to let the upper function be f and the lower function be g. This area is always going to be strictly positive. Now, realize, of course, from the formula that this represents the net area of the function f, and this represents the net area of the function g. So why should it come up positive? Well, because the graph of f is above g, then we know that the net area for f of x must be greater than the net area for g of x. And so the area between the two curves will come out positive. Let's take a look now at example 1. In example 1, we're asked if we can find the area between the curves given by the square root of x here on the top and the line y equal negative x divided by 4 here on the bottom. They do intersect at the origin. However, as you look at this, notice that the area between the two is increasing as you move to the right. And we are not given an interval over which to integrate. Because I know what the line is going to do, as x goes to infinity, it goes to negative infinity. And I know what the square root's going to do. As x goes to infinity, the square root of x goes to positive infinity, which means these graphs are growing apart and the area is getting larger and larger. If I were to try to find the area between these two curves from 0 to infinity, well, it's simply getting bigger and bigger and bigger, and I cannot find it. I need a finite interval over which to integrate in this case. In Calculus 2, we will take a look at some times where we can actually integrate to infinity. But there are particular types of functions where that area is finite, and this is not one of them. So the answer here is no, and the reason is the area grows without bound. And we have no finite interval over which to evaluate. Let's now take a look at example 2. Example 2 uses the same two functions, square root of x and the line y equal negative x divided by 4. But this time, it gives us a bounded finite interval over which to integrate from 0 to 6. That means that when I look at these, what is binding the region are the graphs. Square root of x on the top, the line on the bottom, and the vertical line corresponding to b equal to 6. In this case, we have a vertical line at x equals 0 as well, but the two curves intersect there. So we're actually finding the area from the intersection on the left to the vertical line on the right. It is a closed region. I like to say that it holds water. If you pour water into that area, it will stay there. It has no way to escape. A good way to find the right region is to outline the curves in a different color to highlight them. If the region doesn't hold water, you've got the wrong region. In order to find the area, it needs to hold water. Let's now go ahead and find the area between these two curves by integrating. In this case, what we can do is say that the area between the curves f and g is the integral from 0 to 6 of the upper function, the square root of x, minus the lower function, negative x divided by 4, and dx. Remember, the difference in the two functions is the difference in their y values, which gives you the length of the strip. It's always a good idea to go ahead and draw a strip. Label the small end with the differential. In this case, it must be dx. Notice that as we move from the left side to the right side, no matter where I draw the strip, I always have the same function on top and the same function on the bottom. It's always the square root touching the top edge of the strip and always the line touching the bottom edge of the strip. That tells me that I'm going to take the square root minus the line. Notice that the formula has subtraction in it, so the negative on the line does not count for that, which gives us a double negative, which we change to addition. Go ahead and pause the video, work out the area between these two curves, then turn the video back on so we can compare. So let's see what you got. You're now an old hand at integrating. So hopefully when you got done, even though this got a little complicated at the end, notice that you got the square root of 6 cubed, and that gives us 3 6s under a square root. So one of them pops out and leaves one behind. And we have 2 times 6 divided by 3, which gives us 4 square roots of 6. And the second term gives us plus 9/2. This gives us roughly about 14.3 square units. Let's now notice that the lower limit of integration is the left endpoint given by the point where they intersect and also told to us. And the upper limit of integration is the right endpoint of the interval over which we're integrating, which again was given to us. In this case, we took the upper function, the function that was above when we looked at the graph, and we subtracted the lower function from it. Notice that in the strips, it's always the same function above and the same function below. If that changes, we have to split it into different regions. Now let's take a look at the applet on Desmos, and you can see here the same area. First, you can find the area that is underneath the upper function here labeled f, which comes out to be about 9.6. The lower function, the area is going to be negative because it is below the axis. Its net area is about negative 4.4. And then using a Riemann sum, we can approximate the area between them. And you can see here it comes out to be about 14. Well, I guess it should be, this is 0.02, which of course is getting closer. Now, how could we make it get even closer? By using the applet. We need more boxes, so we come up here to n, and we slide it as far to the right as we can, using 500 boxes. When we use 500 boxes, we now have the approximation 14.27, which is our about 14.3. Let's now take a look at another example. In example 3, we want to find the area between two curves given by x cubed and the graph of the line y equal x. However, we are not told over what interval to integrate. So this means that they must intersect. And we're looking for the area between the curves between the intersection points. However, we have a little bit of a region problem. In the region on the left, which is shaded in green, you can see that the cubic function is above the line. However, on the right side, in the purple shaded region, the line is above the cubic function. This gives us a compound region. When the function that is above changes, you have to split the definite integral at that location. What we're going to do is we're going to draw the strips to help us determine which one's on top and which one's on bottom. again, we start at the left side and we can draw these small vertical strips from the far left to the far right. When we do that, we notice that which function is on top changes when x equals 0. In order to find the intersection points, what you want to do is find where the two functions touch by setting them equal to each other. Do not divide by x. If you divide by x, you are saying that x is not 0. But it is clear that 0 is a place where they cross, and it is in both functions. Do not divide by the variable. Instead, move all terms to one side and then factor. This gives us the difference of two squares, and we can factor that to obtain the three solutions, the three places where there is two graphs cross. X equal 0, x equal 1, x equal -1. In order to find the y value, you can take any one of the x coordinates and put them into either function, because these are where the functions touch. So in this case, 0 must relate to the ordered pair 0, 0. And I'm simply using the identity function y equal x to find it. The second one must be at 1, 1. And the last one is at -1, -1. You can label these on the picture. It may help you to realize how to integrate. Once we have these labeled, we need to figure out which function is on top and over which interval. Between x equal -1 and x equals 0, the cubic is on top. The interval over which we're integrating is the independent variable, which is x. So between x equal -1 and 0, I'm going to integrate so that I have the cubic on top and the line on the bottom. This gives me x cubed minus x dx as the integrand. Now I need to find the area on the other side. In this case, the line is above the cubic. So I'm going to add the area between x equals 0 to x equal 1 of x minus x cubed dx. To get the area to come out to be strictly positive, you have to be careful to always take the above function minus the below function when you're integrating with respect to the independent variable, here x. Go ahead and pause the video now to work this one out, then turn it back on so we can compare our answers. Again, we set up the integral so that the lower limit of integration is the left endpoint. The upper limit of integration is the right endpoint of the interval over which we're integrating. We had to split this one in two regions because the function that was on top and the function that was on bottom changed. This gives us a compound region, which has to be done as separate integrals, although the antiderivatives will be, well, opposites of each other. In this case, for the first, we get x to the fourth divided by 4 minus 1/2 of x squared between -1 and 0. And then we have the opposite, 1/2 x squared minus 1/4 x to the fourth between 0 and 1. Substituting in the values and combining our terms, we end up with 1/2 of a square unit. Let's look back at the picture and see if we buy this answer. Keep in mind that a square unit on this particular graph is the area inside this yellow region. Do you buy that the green area plus the purple area is half of one of those? It seems relatively reasonable, and the calculus is correct. So I know that's the exact amount of area between the two curves where they intersect. Let's now take a look at the next example, which is number 4. In number 4, we have two sine functions. the sine of x, which is graphed here in black, and we have the sine of 2x, which goes twice as fast and is graphed here in red. We want to find the area between the two curves over the closed interval from 0 to pi. And these are graphed only between 0 and pi. We need to find where they intersect. We know that on the far left, we'll use 0 for a lower limit of integration. And on the far right, we'll use pi for an upper limit of integration. But it is clear by looking at the picture that which function is on top and which function is on bottom changes where they intersect. We need to know what the value of that point is. Now, I've provided it in the picture, but how would you find it if you didn't know that? In order to find it, we need to set the two graphs equal to each other. Now, the problem is that one of them has an argument of x and the other has the argument of 2x. To solve this, make a substitution using the double angle formula. In this case, the sine of 2x is equal to 2 times the sine of x times the cosine of x. And we have a sine of x on the opposite side. Remember, I said do not divide by anything with a variable in it. If it's a constant, you're allowed to divide by it. But if the variable is in it, do not. Move everything to one side and factor. In this case, I can rewrite it as sine of x minus 2 sine x times cosine x. Now it's equal to 0. I factor out the common factor of sine x, and this leaves 1 minus 2 cosine of x. Now I can set this up to solve. I need to know when sine of x is equal to 0 and 1 minus 2 cosine x is equal to 0. When I think about the interval from 0 to pi, I know that the sine is 0 at both 0 and pi. I can go ahead and write those solutions down now. And in fact, that corresponds to the left endpoint and the right endpoint where the two curves clearly do touch. Now, what about the other factor? Setting 1 minus 2 cosine of x equal to 0, I end up with cosine of x equal to positive 1/2. Now, cosine over the interval from 0 to pi is only positive from 0 to pi over 2. And that tells me that it's got to be in quadrant 1. The value of it is 1/2, which tells me it's a 30, 60, 90 triangle. Since cosine relates to x, this has to be a skinny, tall triangle. Remember, you can always draw the triangle to make sure that you have it right. This side would be root 3 over 2, and this side would be 1/2. That angle must be pi divided by 3, or 60 degrees. Note that in calculus, our formulas are set up for radians. We always do the calculus with radians. Now that we know the 3 places where the graphs intersect, we can set up the 2 integrals. We're going to integrate from 0 to pi over 3. On the first one, when we draw our strips from the left to the right, notice that the red graph, the sine of 2x, is always on top. So from 0 to pi divided by 3, we're going to have sine of 2x minus the sine of x. And our differential is dx. Now we have to figure out what's on top and what's on bottom in the second region. In the second region, it is sine x that is above sine of 2x. And again, by drawing vertical strips from one side to the other, you can tell that what's on top in that region and what's on bottom doesn't change. And this will give us the integral from pi over 3 to pi. This becomes sine of x minus the sine of 2x. with respect to x. Notice that we are integrating over the entire interval from 0 to pi, because this goes 0 to pi over 3, and this picks up at pi over 3 and goes to pi. Go ahead and pause the video now to work this out. Then turn it back on, and we'll check your answer. Let's see how you did. We have the two integrals written here, separated because there's a change in which function is above and which is below. Notice again that the limits of integration go from the left at the lower to the right at the upper. And in the integrand, we must have above minus below. When we integrate, we need to use either a trig substitution for the double angle, and then use substitution, or just use substitution directly. Both the integral on the left and the integral on the right are the integral of sine of 2x, but with different limits of integration. But because they're both sine of 2x, I can make the substitution in both that u equals 2x, compute du to be 2 dx, and the differential dx to be du divided by 2. And I switch the limits of integration in both. On the left, from 0 to pi over 3 changes the limits of integration to 0 to 2 pi over 3. On the right, pi over 3 to pi changes the limits of integration from 2 pi over 3 to 2 pi. Now it is a function of u. The middle two, however, are still functions of x that we can integrate directly. The antiderivative of sine is negative cosine, because the derivative of negative cosine is sine. Now we can go ahead and evaluate those separately. I'll scroll up so that you can see some of my work here. You have to be very careful with the negatives in this particular problem because there are a lot of them, and it can cause problems when you miss one or two. Go ahead and integrate each one. Don't forget that in the two outside ones where we did use substitution, we'll have an extra factor of 1/2. When you evaluate at the limits of integration, you end up with a positive 3/4 for the far one on the left and another positive 3/4 for the far one on the right. In the middle, you get minus 1/2 and plus 3/2. When you combine it together, you get 5/2 square units, or 2.5. Let's take a look at the graph and make sure that we buy the answer. Coming up here, I'm again going to shade what is essentially 1 square unit. This is 1 square unit. Do you buy that the area between the two curves is 2.5 of those? It's definitely more than 1. 2.5 seems, well, a little bit of a stretch to me, but I'm not very good at judging area. It does seem like it's probably reasonable. It's probably close to around 2 or a little bit more, so 2.5 sounds accurate. Let's now take a look at the next example, example number 5. In example 5, we want to find the area of the region bounded by the curves given by the x-axis, the graph x squared minus 4x, and the graph 2x minus 8. This time we're not told to find just the area between f and g. We're told that we also want to use the x-axis as a boundary. This may change the area that we're looking for. Let's see how that might happen. If we were only looking for the area between f and g, it would be this narrow crescent shape that you see here. But that doesn't include the x-axis. And the directions are clear that they want the region bounded by the x-axis, f and g. To find it, let's highlight the 3 curves. Here is the x-axis. Here is the parabola given by x squared minus 4x. And here is the last one. I'm looking for a region that touches all 3 curves and holds water. This region is clearly bounded, but it doesn't touch the x-axis. That's not the one I'm looking for. This region in here, however, touches the x-axis above. On the left, it touches the parabola, and on the right, it touches the line. The region we're trying to find the area for is the yellow shaded region here. Now let's draw some strips so we can determine which function is on top and which function is on the bottom. Again, we draw from the left endpoint to the right endpoint. We've only discussed integration with respect to x at this point. We'll find later that this problem can actually be done more easily by doing it with respect to y, and I'll show you why. Let's take a look now at what we have in our strips. We can see that we always have the x-axis on top. And the graph of the x-axis is simply y equals 0. So we always have that y equal a constant 0 on top. But the bottom changes. On the left side of where the line and the parabola intersect, it's the parabola that's on the bottom. On the right side, it's the line. That means because we have a change that we have to write it as a compound area. We're going to have to split this right here where they intersect. And then we're going to have to find the area on this side and add it to the area on this side. In order to do that, we need to know what this point of intersection is. It's where the parabola crosses the line. So to find that point, we set the parabola x squared minus 4x equal to the line 2x minus 8. Again, move everything to one side and combine your like factors, or terms rather, and then, if possible, factor it. In this case, it does factor. This gives us x minus 4, x minus 2. This gives us two places where they intersect, at x equal 4 and at x equal 2. Now, we also need to know what the left and right boundary points are, where in fact the parabola is intersecting y equals 0. But we can tell, and using our knowledge of the parabola, we know it's got to be at the origin, 0, 0. If you're not sure, you can go ahead and solve for it by setting the parabola equal to 0. Remember that the x-axis is the line y equals 0, horizontal. This, of course, would give you two intersection points, one at 0 and the other at 4. When we look at the graph, we can see that, in fact, the parabola does intersect the axis again at 4. And because the y value is 0, these have to be 0, 0, and 4, 0. Does the line go through that point 4, 0? We have to be sure that they're all intersecting there. Since we know that the x-coordinate is 4, substitute 4 into the line to see if you get 0, and you do. That means that we have an interval from 0 to 2, and then we have another interval from 2 to 4. Now that we have the intervals and we know which one's on top, we can set up the two integration formulas. In this case, we want to integrate from 0 to 2, left endpoint to right endpoint of the first region, with the y equals 0, the x-axis on top, which is 0, minus the parabola on the bottom. To subtract the parabola, note that you have to put the whole thing in parentheses with the minus on the outside. You need to change the sign of both terms. The second one is going to go from 2 on the left to 4 on the right. Again, it is the x-axis, y equals 0 on top, which has equation, well, 0, minus, this time what's on the bottom is the line. Again, be sure to put it in parentheses with the differential on the outside. Now, go ahead and pause the video, work it out, and then come back so we can check answers. So let's compare. In this case, we can go ahead and simplify the integrand before we integrate. And this will give us negative x squared plus 4x for the first integrand, and for the second, negative 2x plus 8. And we apply the power rule for integrals and substitute in the limits of integration. When we simplify, we get a result down here of 28/3, which is, well, 9 1/3. So 9.3 repeating square units. Let's take a look back at the graph, find out what 1 square unit looks like, and judge whether or not we think 9 1/3 is a reasonable result. When we scroll up, 1 square unit is going to be this little block right here. Do we believe that there are just over 9 of those present? Well, there's 1, possibly 2, almost 3 there, 4, 5. Gosh, it looks a little large to me, but well, the calculus works, so it must be correct. Let's go ahead now and take a look at the last example. Oh, wait, before we do that, let's talk about why this might be easier to integrate with respect to y as opposed to x. If I take off the part that I have on the inside, and I look at this graph with respect to y, meaning that I would have to solve the two equations for x in terms of y. In other words, instead of y equals something with x, it will have to be x equals something with y. And then, instead of drawing the strips vertically, I would connect them left and right. When we go with respect to y, it's left, right, not above, below. That means that when I draw my strips from the top to the bottom, I have to have the strips be horizontal. In this case, the narrow end of each strip is vertical, which means that the differential would be dy, which matches if I'm going to solve for x in terms of y. Notice that in this case, the parabola is always the function on the left, and the line is always the function on the right. If we integrate with respect to y, we will not have to split it into two regions. Now let's turn our attention to the last example in this section. This is the graph of x to the 2/3 power, which has a cusp here at the origin. The other graph is the horizontal line y equal to 4. We want to go ahead and integrate this with respect to x. That means drawing the strips vertically so the differential, the narrow end, is dx. When you look at this and you go from the left to the right, does what's on top and what's on bottom ever change? The answer in this case is no. Now, how can you find the 2 points of intersection? Again, you have to set the equations equal to each other and solve for the x coordinate. I'm going to let you work on this one on your own. When you're done, come back so that we can compare our results. So let's go ahead and discuss this example 6. Notice that we do have an even function here, that it is in fact y-axis symmetric. I use this in my integration to make it a little bit more simple. I went ahead and outlined the two graphs here to find the region that held water, which is the yellow shaded region you see here. And I drew vertical strips from the left to the right to determine if I always have the same function on top and the same function on the bottom. The function on top is the horizontal line y = 4, and the function on the bottom is always y = x to the 2/3 power. In order to find the points where they intersect, I need to go ahead and set the two equations equal to each other. In order to solve for x, I have to undo the 2/3 power, which in this case means raising it to the 3/2 power, since 2/3 times 3/2 gives me 1. When I do this on both sides, I get 4 to the 3/2 power, which is the same as the square root of 4 raised to the 3rd power. However, note that this only gave me one of the solutions. It gave me the one on the right. But because I know it is an even symmetric function, I know that I must also have an intersection at -8 on the left. And I can always check that in the function by substituting -8, squaring it to get 64, and then taking the cube root, which gives me 4. This gives me my two intersection points, which will become the limits of integration. The left endpoint is -8, and the right endpoint is 8. This time we don't have a compound region, it's 1. We take the above function, y = 4, and subtract the below function, x to the 2/3. Then I use the fact that it was y-axis symmetric to rewrite it, since I had a symmetric interval from -8 to +8 across the origin. I rewrote it as 2 times the integral from 0 to 8. That's not required. You could have left it this way and integrated with that. It's just simpler when one of the limits of integration is 0. And it's simpler than having to deal with a negative number. In this case, when I integrate, I apply the power rule. I went ahead and simplified and distributed the 2. Remember that when you divide by the new power 5/3, it's the same as multiplying by the reciprocal 3/5. Then the 3/5 times 2 gives you 6/5. Then you substitute these values in the limits of integration into the antiderivative function. The first term gives me 64. The 5/3 power is the same as the cube root raised to the 5th. Again, we do the root first to make it smaller before we blow it up, because I don't know what 8 to the 5th is. And even if I did, I wouldn't know what its cube root was. But I do know that the cube root of 8 is 2, which gives me 2 to the 5th. And I know 2 to the 5th is 32. When I work this out, I get 128 divided by 5, which is 25.6 square units. Let's go back and check and make sure that this seems like a reasonable answer. In this case, if I'm to highlight 1 square unit, I may have to do it in a different color since it's very small. That single block of blue there is the size of 1 square unit. And I do have quite a few of them in here. 25.6 sounds reasonable. Now, we've been working all of these with respect to the independent variable x, but it's time to talk about some that are done instead with respect to y. If we're going to integrate with respect to y, then the equations have to be written in terms of y, meaning we have x equal an expression of y. The differential will have to be dy, and the limits of integration will have to be y values. So the lower limit of integration will be the lowest y value of the region, and the upper limit of integration will be the highest y value of the region. And instead of looking for an above function minus a below function, we'll look for the right function minus the left function. We're going to stop here and split section 6.1 into 2 videos. There's a lot to cover and we don't want to rush it. In the next video, we'll take a closer look at integrating with respect to y and determining which one might be easier or if they're both equally the same. See me for the next video.